Okay. Okay. Right. What am I looking at now? Now, let me just bear with me for a second. I'm going to have to try and get this, that the font size can be improved upon. Bigger. Okay. 18. Yes. Yeah, I can go with that. Highlight. Let's try yellow highlight. Yeah, okay. Okay, let's see if that gives me what I want. Let's hope it does. Right, what I want to look at here is production of an EMF, okay? And that is just production of an EMF, okay? And that is what we're saying here, okay? Yep. Again, I'm going to highlight and yellow, okay? And that gives us a bit of perspective. And here we can just simply put the font color in on this instead. And make that 14, I think. Can we get away with that here? Yeah? Yes, I think we can get away with that. Yeah. Okay, good. Now what I want to do is to look at okay, let me just make him a little bit larger, okay. 16 as well. And the font type, let's bring in the, I'll go with the bold. Nope, 2. Has to be lighter, hasn't it? Okay, that will be it, I think. Now again here, I'm just showing you, sorry, I've dropped out. Okay, so what I want to do here is to make that 16, okay, and bold, so it stands out, okay, and yeah, that will be about it, I think. Yeah, okay. Now what I'm trying to do is to make this more visible, so it's easier to read. That's what I'm trying to achieve, but I probably should have done it before I started working on it, but these things happen. It's just that I'm in the frame of mind now, you see, to deal with this, whereas before I wasn't quite so sure. Okay, I was more inclined to go to sleep actually, to be honest with you, but somebody has to do the hard graph. Bring it to 16. Okay, yep. Okay. Here is where I want to be able to make this affirmatively larger. I'll bring that up to here. Okay. Bear with me for a second and bring that up larger as well. 16. Okay. And bring that into the spotlight. Let me just break them down a little bit. So we have a space. Okay. That's the idea here. Now batteries are free. Right, now let's look at this information on batteries. We can make that large. Okay, so let's make that larger. That's 22. It's large wrong. Okay. Okay. And we'll make the U again that. Okay. Now let me just take it to the top. Bear with me for a second and I'm going to work my way through. Okay. Right, what I wanted to look at is to look at production of an EMF. Okay. There is more than one method of producing an EMF and generating current flow. The methods we are going to look at in this section are chemical, magnets, and thermal. Note: at this point, it is worth noting that although EMF is an acronym for electromotive force, force has since been clearly defined in the world of physics and is actually a force in the physical sense. It is important to remember what EMF means, but we shall refer to it only as EMF for the remainder of this document. Okay? Okay? The magnetic generation. In simple terms, electricity can be made or generated by moving a wire conductor through a magnetic field. And this is what we're looking at, that field. A magnet produces a field which can be best demonstrated by using a standard bar magnet, a piece of paper, and some iron filings. The filings will arrange themselves around the magnet lines of flux as illustrated in the diagram on the right. And this is your diagram here on the right. Okay? When we place opposing poles within a controlled environment, and that's our magnetic field, north and south, we will get the magnetic line of flux, but this time the forces flow from north to south, as illustrated on the left. When a conductor passes through these lines of flux, it knocks the loosely held electrons out of their orbit, creating a current flow. If the conductor is part of a circuit, this is often referred to as cutting the lines of flux. Once I can make this big enough. Let me see if I can make this bigger. I want to be sure that it can be seen by everyone. Okay. It's clean. Okay. Yep. Okay. A simple example of this can be seen in the following diagrams. A single stationary coil is placed between two static permanent magnets with opposite poles facing. A single coil of wire is placed between each magnet and positioned at right angles to the magnetic flux. At this point, no EMF is produced in the single coil of wire. If we were to rotate the coil so that it's seen to be cutting through the magnetic line of flux, a voltage is immediately induced in the coil. The amount of EMF supplied is relative to the speed the coil is rotated and the density of the magnetic flux. The stronger the magnet, the higher voltage generated. Okay. Generation and distribution of the majority of major power is based upon this principle, which form the very fundamentals of electrical generation. Okay. Chemical generation, very simply, chemical generation is where two metal electrodes are immersed in an electrolyte. Examples of this are batteries and fuel cells. The makeup is different depending upon the application, but the fundamentals remain the same. The concept is based upon the voltaic pile, an experiment conducted by Alessandro Volta, which consisted of zinc, blotting paper soaked in salt water, and silver or maybe copper. When he attached a wire to the top and bottom disc, which must be different metals for it to work, he measured a voltage and a current. He found that the pile could be stacked as high as he liked, and that each additional layer increased the voltage by a fixed amount, depending on the metals he used. The current is produced because of a chemical reaction arising from the different electron attracting capabilities of the two metals. Battery and chemical reaction. Batteries have three parts: an anode, a cathode, and the electrolyte. The cathode and anode, the positive and negative side of at either end of a traditional battery, are hooked up to an electrical circuit. Okay, and I hope you found this useful. Okay, let me just go back up, make sure that we can get this all into view. Okay. Thank you. Okay, have a good day. Bye bye.